infinite number of them. That's another famous proof. I won't do it here, but in number theory, you use proof by contradiction to prove that there is no maximum prime number. Okay. Anyway, so which came first? Was it Pythagoras at school, or Euclid, or maybe I don't know enough history of mathematics. Anyway, so I assume the school, the group of Pythagoras, found this proof and were very disturbed by it, particularly Pythagoras. And so the group, they all made an oath. They swore that no one within the group would tell people outside that that the square root of 2 was in fact not a rational number. That was very disturbing. This cult almost, this group of Pythagoras, it was almost like a religious cult, but based on mathematics, based on integers. So it was a kind of, what's the word when you play around with numbers? A numerological religion, right? Sort of. Okay, so they made this oath under threat of death. Anyone who divulged the secret that square root of 2 was not a rational number, that person would be put to death. Well, one of them did, and he got drowned. Right? That's the story. Okay. All right. So how to prove that square root of 2 is not a rational number? Okay. So firstly, what? Now need a technical term, a label. A number that is not a rational number is called an irrational number. The IR here, just another way of saying not rational. Okay? So irrational number. So the theorem statement, a theorem, okay, and here's your theorem statement, root 2, square root of 2, is an irrational number. And we're trying to prove that. So this is your mathematical statement P. Okay? But P is all this. Root 2 is an irrational number. That's your P, mathematical statement. And how do you prove that this is true? Well, we will use a proof by contradiction type argument. So we will start with the opposite. We will contradict P, we'll contradict this. In other words, we will be saying that square root of 2 is a rational number. Right? That's the contradiction. Now, so from that we will deduce something. We will deduce Q, and we will find that actually not Q is true. So we've got to contradict. Sorry, we know that not Q is true, but we deduced from not P. We deduce Q, but we know not Q is true, and therefore not P must be false. Using the modus tollens that we talked about previous session. So not P is true, and therefore P is true. And what's P? Well, this. Okay, so that's our proof. That's the grand strategy, if you like, the overview. All right. So now we have to actually make the deduction, assuming not P, assuming not this. In other words, root 2 is a rational number. Right? That's the not P. From that we will deduce something Q, and but we happen to know that not Q is true. So therefore Q is false. And if Q is false, then not P is false. Therefore not P is true. Therefore P is true. Right? Okay, so let's assume, it's a proof by contradiction. So what we're trying to prove here, P, let's assume not P. So not P. Okay, we start with that. And so that is root square root 2, or root 2 is rational. And that means you can write root 2 in this form, rational numbers. And remember, if this is a rational number, m and n, we assume, have no common factors. That's important, right? Because we'll use that later. Okay, I emphasize that. So m over n are integers. N is non-zero, and m and n have no common factors. Right? That is your we'll just remember that, and that'll be related to our Q and not Q. You'll see how it all comes in a minute. Okay, so m and n have no common factors. All right. So square root of 2 is m over n. Okay, square both sides. So the square root of 2 is just 2. The square root of this is m squared over n squared, and therefore m squared equals 2n squared. And that means that m squared is even, right? Because it's 2 times some integer. So m squared is even. Now if m squared is even, m is even. You could prove that if you like. Seems to be like it's fairly obvious. If m is odd, we're talking about integers. If m is odd, m squared is odd. Okay, but m squared is even, so m is even. In fact, there alone is a little proof by contradiction. Okay. So if m squared is even, m is even. All right. So that means you can write m as 2 times some integer, right? Because m is even. This is even. 2k is even. So m is 2k, right? Where k is just some integer. It belongs to big Z. All right. Okay, so I've got a formula here for m. It's 2k. Plug this 2k into here. So you get 2k all squared is equal to 2n squared. Okay? So 2k all squared is 2n squared. And that implies, so this would be 4k squared. Divide both sides by 2, so you get 2. N squared is 2k squared. N squared is 2k squared. Well, that implies that n squared is even, right? Because this is even, right? Because of the 2. So n squared is even. So that means n is even. The same logic as here. So if n squared is even, n is even. All right. So that means you can rewrite n as 2 times j. J is just another integer. Okay? So n is 2j. So in other words, that means. Now m we found was 2k, and n we've just found is 2j. Okay, so you can rewrite m over n as 2k over 2j. Ooh, look, we have a common factor. That's a contradiction. Right? We assumed mn have 0 common factors, have no common factors. Now p. The statement we're trying to prove, p is, root 2 is an irrational number. Okay? So we assume the opposite of that, not p, and that is, root 2 is a rational number. Okay? And from that we deduce q. Now what's q? Q is, root 2 has common factors. When it's written in this form, it does have common factors. Right? But that's a contradiction to the idea that m over n has no common factors. So you've got a contradiction, and so the fact that has two as common factor, that is a contradiction of the idea that m over n have no common factors. Okay? So we've shown that this does have common factors. And therefore the not p is false. Okay? Yeah, not p is false by modus tollens. Therefore not p is true. But not p is just p. And hence you proved this, because this is your p. Alright? Well, it's the sort of just saying down here. Okay? So if p is a rational number, then that means that m over n we deduce that m over n is not rational because it has common factors. Okay, so m over n is not a rational number because it has common factors. So so not of P implies that P is not rational, okay, or, and hence P is irrational. Okay. Alright. Now the next one, the third one, the proof type, a way of proving, a method, proof method. It's called proof by induction. It's a bit more complicated to explain what it is compared to the others. So it's probably easier. I was debating how to do this. I wasn't too happy with the way Sipser did it, so I compromised. What you're getting here is a mix of me and Sipser. Now his big example, like 2 sessions from now,